In heavy mechanical systems, the forces keeping things perfectly still are often just as violent as the forces tearing them apart. You simply cannot see the extreme tension building between these microscopic surfaces until the exact moment it suddenly snaps. If you are studying introductory mechanics, you have almost certainly memorized this equation. Too many students treat F equals mu n as a constant, absolute state of friction. It isn't. When Coulomb formalized the laws of dry friction in 1781, he established that frictional force always opposes impending motion, and it scales proportionally with the normal force pressing the surfaces together. The crucial detail that often gets lost is that static friction is purely reactive. To map out exactly how static friction behaves under an increasing load, we plot the frictional force against time as an external push steadily increases. This chart reveals a rising linear slope. In this variable zone, static friction perfectly matches whatever applied force you push with, pound for pound. It simply outputs whatever resistance is required to maintain a zero net force, keeping the object completely stationary. It only reaches its mathematical limit at this highest point. This is the boundary condition, representing the exact threshold of impending motion. This single, highly specific moment is the only time the equation F max equals mu n is actually true. Push even a fraction harder, the boundary condition breaks, and the object slides. The resistance instantly drops off into a lower, constant state of kinetic friction. Therefore, in any physical state prior to the exact threshold of slipping, applying the static coefficient will generate phantom forces that don't physically exist. You must calculate the actual friction by setting the sum of all forces to zero. We can prove exactly why assuming constant friction fails by examining a classic engineering test case, a 500 Newton block resting on a 30-degree incline with a coefficient of static friction of 0.3. We apply a horizontal force, P, directly into the slope. Our objective is to find the exact force limits required for the block to either resist falling down the slope or to just begin moving up the slope. For impending motion down, gravity pulls the block downward, so reactive friction points upward to assist our push. Resolving these forces to zero reveals the minimum force required to stop the fall is 120.1 newtons. At the opposite extreme, impending motion up the plane, we aggressively overdrive our push. The friction vector actively flips 180 degrees, pointing down the incline to resist. Solving this boundary condition yields the maximum force to move the block, 379.9 newtons. This number line highlights a massive mechanical deadband. If you apply any horizontal force between 120.1 and 379.9 newtons, the block does absolutely nothing. It remains perfectly static. Inside this static deadband, the friction vector varies continuously. It drops from maximum upward, passes completely through zero, and grows to its maximum downward value. It does whatever is required to balance the forces. Using F equals mu n inside this deadband breaks the physical laws of statics. The equation is strictly a tool to locate the outer walls of the deadband, not to describe the reality within it. We scale this specific boundary logic to evaluate complex mechanical advantage devices, where engineers lift immense loads using minimal effort. This is a classic double wedge system. Our goal is to find the smallest horizontal force, P, required to drive the bottom wedges inward and force the heavy load overhead to lift. Because we are calculating the exact moment of lifting, we are sitting directly on the boundary condition. Motion is impending everywhere at once. Therefore, we are allowed to use our maximum friction equation at all contact surfaces. You must mathematically shatter this complex machine, isolating components into distinct free body diagrams. Isolating the top block, we align normal forces perpendicular and point friction downward to resist the lift. Balancing these equations yields the downward normal force, exactly 853.33 newtons. Crossing the shared boundary, that 853.33 Newton normal force transfers directly to the wedge's top surface. Summing the forces on this component, including ground friction, isolates the exact effort required to drive the entire system, 524.5 newtons. Solving any complex mechanism relies entirely on enforcing local equilibrium at these isolated contact boundaries. You construct the machine mathematically, piece by piece. Throughout history, engineers have manipulated physical laws using simple machines. But whether you analyze levers, pulleys, or wedges, they are all governed by the exact same geometric principles. The ultimate evolution of the wedge is the screwjack. It can lift tens of thousands of newtons of load with very little human effort. Mechanically, a screw is a continuous inclined plane wrapped around a cylinder. When unwrapped, these dimensions map straight to statics equations. The height is the pitch, the base is the circumference, and the slope is the angle of inclination, alpha. This geometry governs the most critical safety feature of a lifting screw, the self-locking condition. It ensures that when you remove your hands from the tool, the massive overhead load doesn't backdrive the screw and crush whatever is beneath it. The system remains securely self-locking as long as the angle of the thread, alpha, is less than or equal to the angle of friction, phi. If the slope is designed shallow enough, static friction alone provides the holding power. In machine design, friction is never a constant variable you mindlessly plug into a calculator. It is a highly adaptable, purely reactive boundary condition. The math requires strict discipline. Draw the free body diagram, properly define the direction of impending motion,